able to know the 5-number summary quickly and easily. As always, least to greatest. Laura, 1,000 points right there. And let's do this.
I found him. What's he doing? I don't know.
The 5-number summary is the following values.
He's talking to someone.
From least to greatest, min, Q1, median, Q3, and the max. Nice answers. If you put the 5-number summary in the chat, you get 1,000 points. Keep these answers coming.
What is it? What happened?
Hey everyone, how are we doing? We're gonna start here with the little 320. I'm feeling a good bit better, coughing a lot less. Maybe it's all the Monster energy drink. Still no fever, still no COVID, probably just a cold. I'm like, don't cough, Brian, don't cough. It looks bright lights in here, all the bright lights. But if you're in the chat, feel free to say hi. Morning, Noel, good to see you. We're gonna do a little 320 to start. Evan sent me some code. So here we go, BAS 320 wine assignment. Let's take a look at what's going on here with this code. So Evan said, can't go over this code during office hours, so he's given me the permission to look over it. And let's take a look what's happening here with this code. Evan, what's up? Good seeing you there, seeing all the students. We got loading library reg class right here. We got loading cable extra. We're loading the EX6 wine data. We're selecting only certain variables right here. Creating a data dictionary to talk about them. And then the data dictionary right here, cable, HTML, escape equals false. I don't know what that does. And a style of the table to make it look all nice and pretty right there. Row spec, that controls how the rows look on a certain thing. The column spec controls how the columns look, so looking good. Man, this is really pretty. And you can actually collapse these. I don't know if you knew that, Evan. You probably did it this way, but you can actually collapse them with the way you've done this right here, and you can search through your document. All these are untitled, but if you go inside of here, you can actually start titling things, but you can go through and search through the document. So I think if you go and call this like plot stuff, I think if you do this, I always forget how to do this. No, it's not coming out. It's untitled, so it's registering it here. So what if we take this and we say plot stuff here? And what if we do that? We'll do it? No, it doesn't do it. It's mad. It took away that it took away that. So whoa, what am I doing? Ah! Okay, let's stop. Let's stop destroying things. Control Y, Control Shift Y. I'm destroying things, Evan. We don't need these. These are just section blocks. Okay. It's looking pretty good. The last code was an attempt to make an interaction plot having multiple variables in one, so ignore the very last code because I don't think it worked. Which line of code do you want me to go to, Evan? What line of code do you want me to start looking at here? I see a lot of good stuff in here. I see summary tables. Yeah, that's how you want your summaries tables to look. Once again, if you're wondering, especially for 320, if you're in my section, I don't want you to make summary tables that look like the following. You do not want to do a summary table that looks like the following, where you go summary and you print it out looking like this. This, you look at the first block of code after the data dictionary. Yeah, let's look at that. You do not want to look like this. You want to look like Evan's doing to make it look nice and pretty right there. You want to make your output always look nice. So Evan's doing a great job right here making the output look nice and presentable, because that's half of doing analytics. Half of it's doing analytics, making it look all nice and pretty. So after the data dictionary, okay, so let's go back up here. Here's the dictionary, and that's what the data dictionary is. So you're loading EX6 wine. You're making sure that it's a factor, which you probably didn't need to do, but this might cause problems. So right here, because it's probably AI a little bit, and nothing wrong with AI. Right now, let's look at the quality of wine, and we haven't loaded EX6 wine. We haven't loaded reg class. There we go. Now we can load the wine. Right now, this code actually does nothing. Line 44, which is not horrible, it just does nothing. As in, it is currently high-low. Now, the next line of code is iffy-ish, because possibly, that's totally fine. He's got to know what it does. Got to know what your code does. This says store into EX6 wine quality, a factor of EX6 wine quality where the levels are high and low. So you got to make sure, you see how the last is low, low, low? The worst thing that could happen is if when it overwrites it, okay, it didn't change it. It's fine, it just does nothing. It's already a factor, so it's fine. This is creating a new variable right here that is going to be numeric 1 zeros, which we don't need to do. So actually, I think your code is doing things we don't need to do, because if you're going to use quality of wine to make predictions, you can literally go in here and make a linear model. where we predict something like, I'm going to attach the data frame, which gives me autocomplete options. So if you attach a data frame, you get autocomplete. So if I type residual sugars now, which is in here, I can do residual sugars, tilde, chlorids. Chlorids are lots and little. So we use quality. Good morning, Kylie. We're going to do some 201 here in a moment. So quality plus, and then let's go look at the other variables inside of here. Fixed acidity. So what you'll see right here is we now have a model with a categorical X in it. And the categorical X can be seen with quality low, which you should know is the indicator variable. The reference level is what, Evan? So we don't need to convert cat to quant exactly. To quant like the tech code chapter. Well, so it's done for you. So it is converted. It's converted to indicator variables for you. The code does it itself. So it is converted, but it does it for you. So quality low is the indicator that has been created. And so it's done for you in this line of code right here, line 46, by including quality, which is a categorical variable, it automatically becomes an indicator. And remember, it has two levels, high and low. So the first alphabetical is going to be, and H, I, J, yeah, because H is the first alphabetical, that becomes the reference level. Is this all making sense with the lecture? The reference level is high, and we're predicting the sugar of a wine. And it turns out if it's low quality, it'd be predicted to have more sugar. The reference level is high because it's the first alphabetical. And I would say two wines that are otherwise identical, the wine that is low quality would be predicted to have 1.7 grams more sugar than the high quality wine. So basically they're just throwing some sugar in some low quality wines. You're like, you want some, this monster could be a low quality wine probably because it's got, well, actually it has 0 sugar. So it's high quality. It doesn't work that way. It's not cause and effect. Is this making sense, Evan? This is also a rather surprising model because it is statistically significant, but it only explains about 4% of the variation, which is on stat 201. R squared is blank percent of the variation in Y. It's explained by the variation in the X, or X's in this case. So you want to make these models right here, and then when you visualize it, if we're doing the interaction on this, we have to add a star to it. We can see the significance of the interaction term, and whoa, I have a significant interaction. How do I know that? The p-value on the interaction is significant. Boom, right there. Which means my lines are not going to be as parallel. I would suggest using the base codes to start. So my visualizations, let me see what it says right here. So do my visualizations create what you're looking for in the interaction plot. So this is what you should see with an interaction plot, Evan, something like this. Does this make sense? This is what an interaction plot with an indicator categorical variable will look like. So you need something, so I won't show yours exact ones, but if your plots are looking like this to some degree, where you have two lines, should it just be between the two variables? That is correct. You can do interactions to the higher degree, but it gets way harder to visualize. And so I would only suggest including two variables. Braden, good to see you there. And notice some of this covers what we covered in 201. How would you interpret this R squared? So if you're in 201, remember, we're trying to predict residual sugar. So what would you do for R squared? We're going to start bridging into 201 now. For R squared, how do we interpret R squared? Yeah, I would just use two variables. Use x1, x2, x1, x2 interaction. x1, x2, x1, x2 interaction. So try to interpret that R squared right there. If you're in 201, you're watching this right now, we're right about to start some 201, but how do you interpret that R squared? We should know it. Blank percent of the variation in Y is explained by the variation in X, and all you have to do is change it to X's in this instance. What is the interpretation of R squared? We'll switch over here. So I hope this helps you out a lot, Evan, and I can respond more. But try it. There's the R squared. Literally, it says R squared right here. We use the multiple R squared. You can round it to 5%. And R squared is not R. R squared is not R. So what's the interpretation? 4.896% of the variation in quality can be explained by the variation in the X's in the model. Oh, and it's not quality. Remember, it'll be the Y variable of interest. No worries, Evan. Good work. Let's show you some points. Evan's got the max points. You want to see Evan's got some crazy points. So it'd be 4.896% of the variation in residual sugar is explained by the variation in the X's in the model. And we can just, get the X. And remember, there's more than just fixed acidity. There's also quality. So, and their interaction. That's usually why I just say the X's, because there's 3 X's in the model. There's quality, fixed acidity, and the interaction between quality and fixed acidity, which creates the difference in the slopes of the lines. So understanding interactions with categorical variables create different slopes of lines is very important. And we also covered some 201 topics right here. So let me do some bridging of concepts. So if you're in 201, we're going to switch topics a little bit here. And we're going to talk about regression. So this is Stat 201, regression interpretation views. Interpretation review. Who's in 201? Speak up now. Mebot's about to drop 5,000 points. Oh, I think I hit, no, I didn't hit the button. Who's in 201? Who's in 201? Me, Braden's here. I need you to practice. I was. That's why you're doing so well. David. So, okay, we got some 201. It was me. Kylie's here. So what you're about to see is a regression model. Kenai, good to see you there. So with this, let's review how to interpret regression. Brian is going to make a linear model predicting height from weight from data equals survey 10. I am so sorry, everybody. Don't touch my shoulder. I swear, I'm like, today, I think I'm like an 8.5 out of 10. It's just like, started feeling a little meh on Sunday. So thank you, David, for the bless you. It's like, where do you sneeze? I don't know. Anyways, that's that. Okay. What are the three things you have to interpret for the test? What are the three things you have to interpret for the test? What are the three things you have to interpret for the test? If you sneeze in your hands and you touch everything, don't do that. Shoulder. What are the three things you have to interpret for the test? What are the three things you have to interpret for the test? The slope, the intercept, the r squared. Okay, so where is the r squared in this output? Where is the r squared in this output? Where is the r squared in this output? Mubot is spamming r squared. Evan's doing it, not even taking the test. Where's the r squared? So knowing where r squared is at is very important. So if you're practicing for the test, you should be able to do this. Good, right here. There's r squared. In this output, it's the multiple r squared. We'll usually just call it r squared. So there's the r squared right there. So how do we interpret that? You multiply it by 100, and you look at your graphic with the y and the x. Oh, move the decimals, Evan, a little bit. And, oh, Evan, you took the RMSE. No worries. Evan took the RMSE. No worry. That's the typical miss the model makes. Not talked about in 201, though. We're throwing Evan some points here. You caught it right away immediately, Evan. You caught it immediately. So how do we interpret it? I can do it instantaneously. I can give you every interpretation of every model, but I need you to practice it. I need you to practice it. Mubot is dropping how to interpret it in the chat. It's the pinned comment right now. So I need you to think about how you interpret it, because Mubot has the pinned comment. So you will be typing this out later. So if you know how to interpret it, it gets easier. And r squared is not correlation. R squared is not correlation. R squared is not correlation. I screamed it out. 36% of the variation in height is explained by the variation in weight. Noel, 1,000 points. You got it. That's it. That's Noel on a scale 1 to 10. Marley, good to see you there. On a scale 1 to 10, 1 being super easy and 10 being impossible, how hard is it to interpret r squared? Blank percent of the variation in y is explained by the variation in x. Great job, David, right there. 36.13%. I throw a little percent on there. I would still give it full credit. 36.13% of the variation in height is explained by the variation in x, which is weight in this instance. So I hope it gets easier and easier to interpret these things when you see your r squared right here. Now, if you take a look at this table, people usually get confused by it. 8 out of 10. Oh, but I think it's getting easier, right? Blank percent of the variation in y is explained by the variation in x. If you take a look at this table, notice how, if you trace down, this is the estimate of the intercept. That value I've highlighted right there is what in notation. If you had to write the notation of this, what is that value in notation? When you say explained, remember that like blank percent of the variation in y is explained by the variation in x. So if you say explained really very strong, you'll remember it's y is explained by x. And mixing up x and y won't lose a ton of points. It will lose some though. What is the notation for this value? It's the estimate. It's B0. Great job, Marley. It'd be B0 because B0 is when x is equal to 0. Y is expected to be B0. Well, then the other one is the estimate of the x coefficient, making this down here B1. Take a look at the model. Notice here, and I wish it extended all the way, but if we were to extend this line down further, where do you think this line right here, if we were to extend it further, where do you think this line would hit where 0 is at? if 0 is going to be about here-ish, where do you think that line would hit? So if we have 0 right about there, where do you think that line hits the y-intercept? Just take a guess. Like, at what value of y, like when x is 0, we expect y to equal what? When x is 0, we expect y to equal what? You have to take a look at the y values over here. When x is 0, we expect y to equal what? Just take a look visually. When x is 0, take a guesstimate. We expect y to equal what? It's lower than 60. It's lower, and you might be looking, I see what you've done, don't worry. A lot of people go to right here, but that's not when x is equal to 0. It'd be over here-ish, and it is basically based on my drawing. So a lot of people think, oh, the y-intercept is here, but that's not when x is equal to 0. So there is confusion a lot of times. I've had students make like 98s on the test, and they say, but the y-intercept is right here, but the y-intercept is when x is equal to 0, which would be all the way over there. So that can be a point of confusion, and I totally understand. The y-intercept is all the way over there, where the line would extend all the way over here. So Kylie, you've probably got a good guess, and the answer is, it's actually, I might have not drawn it properly, at 56-ish. So how is this interpreted? How do we interpret this? When x is equal to 0, so try interpreting it, try writing it right now for practice for the test. This is 12 points. How do we interpret it? And then we have to ask, does it make sense? How do we interpret it? So this is your time right now to write an interpretation with what MuBot has pinned in the chat with the intercept. I'm going to pin it right here. So I want you to try to write out an interpretation of the intercept. When x is equal to 0, we expect y to equal b0. When x is equal to 0, we expect y to equal b0. When x is equal to 0, we expect y to equal b0. So what's the interpretation? So you have to remember, when x, which is weight, is equal to 0, and just think about it visually. When weight is equal to 0, we expect height to be, be careful. You have to plug in this value right here just as is. And so when weight is equal to 0, we expect height to equal 56. This does not make sense because if you weigh nothing, you can't have any height at all. And so Braden has done it perfectly. That'd be full points on the test. Look at Braden's answer. And I would maybe carry just a few more decimals, Braden, but if the graders took off points, I would give them back to you. It never hurts. Usually 2 decimals is good. And then I would write out the word equals in your answer, Marley. So good answers. And then I'd mention this is illogical. So Braden has the all-star answer right there. If the graders took off points, I'd be giving Braden back the points. So read it again. Yep, it's just safety. You can always tell me, Brian, I think the graders were mean to me or to your other instructors. But Braden, yeah, that is a perfect answer except for the 2 decimals. When weight is equal to 0, we expect height to equal 56.34 or 35 rounding. This does not make sense because if you weigh nothing, you can't have a height at all. And even that typo right there, I'd be like, rock nose. So really good work. And even right now, try writing what Braden's done because it comes down to practice, and make sure to add in if it makes sense or not. Just that little, is this logical? To figure out if something's logical, you just think, well, if somebody has 0 weight, they don't exist. So it's not logical, and it's an extrapolation of the model. Last but not least, we have the slope. And how do we interpret the slope? The slope is, for each 1 unit increase in x, we expect y to increase by or decrease by b1 on average. This is increased because it is a positive slope. So what I want you to do is try to interpret the slope right now. And be very careful. People get to these last questions and they start just using slope, intercept, r-squared interpretations, but not reading what the question says. If the question says interpret the slope, make sure to do, for each 1 unit increase in x, we expect y to increase or decrease by b1 on average. Do we just write the values as we see it? So if it's a decimal, yeah, it never hurts to carry too many decimals. Graders should never take off points for that. Rounding can be a little bit subjective. So if you're ever concerned, throw a few more decimals on. Like if you're ever like, should I add a few more decimals? Rounding too hard could be a problem. For each 1 unit increase in weight, we expect height to increase by point. Be careful. Height increases by inches, right? Height is inches, though. So we don't have the right answer yet. Keep trying. So for each, I don't want to say it. Do some reworking. Remember, height is in inches, and weight is in pounds. So we got some pretty good answers. Some 3 out of 4 points. So close. Reword the answers. This is practice time. For each 1 unit increase in x, we expect y to increase by b1 on average. B1 is the value highlighted. For each 1 unit increase in weight, we expect one's height to increase by point exactly. David's got full points right here. I'd maybe change for each 1 unit increase in weight for each additional pound somebody weighs. We expect their height to increase by this. Or you could say, you know, I don't want to get into 320 interpretations. But David has a 4 out of 4 answer in my book. And so does Braden, I think now too. For each 1 unit increase in weight, which I'd probably say for each additional pound, because that's what weight is in pounds. For each additional pound, we expect someone's height to increase by 0.0732 inches on average. Does that make sense? And if you look at MuBot's answer, for each additional 1 unit increase in X, we expect Y to increase/decrease by B1 on average. Now, don't write increase, decrease. I have so many students who do that. I'm like, no, you have to see if it's positive or negative. Any questions about these 3 interpretations right here? Any questions about these 3 interpretations? Any questions? Because now let's do the regression equations. The regression equations. So we are going to review the regression equations. Okay. How in the world would we write an equation from this? What is the equation of regression? What is the equation of regression? How do we write the equation? I'll give you a hint. Pretty much, X is the weight, X is weight. So what is the regression equation right here? Can you write it out? Remember, this is B0, this is B1, this is the name of the X variable. Y hat is predicted height. That means predicted height. Nice job. Yeah, there we go. We got some answers in the chat. And so Y hat equals B0 plus B1X. So we go, I'm going to round it a little bit here, 56.34, because that's B0. Notice I'm just plugging them in where they go, plus 0.073, and then we would times it by weight. Does this make sense to people right here that it's the predicted value of Y? Great job, Kenai, right there. Everything. X, aka weight, exactly. And then B0 plus B1X. So great job, Noel. So you're just plugging in the values where they go, like where you see B0 is here. Well, then you plug in the value of B0. Where you see the value of X, which is weight, you plug in weight right there. And this is the general form up top. Like over here, this is the general. And this is for our equation. Like this is our work. Like when we plug in our numbers. And so down here, we could throw in, and purple's not going to look so good. We'll go orange. And this is the slope coefficient. It's called the slope coefficient, or the estimate of the slope. And then the Y variable, we were predicting height, which is not here, but you just have to remember we're predicting height. So Y hat means predicted height. So Brian has a weight of probably 185 these days, 185. Brian is actually 75 inches tall. What is Brian's residual? So what is Brian's residual? Residual, E, so residual equals actual minus predicted. So what are you missing from this equation? What are you missing? To find Brian's residual right now, you are missing what? To find Brian's residual, which is E, what are you missing? To find Brian's residual E, what are you missing? To find Brian's residual E, you're missing my predicted. So how are you going to find Brian's predicted height? So to find Brian's predicted height, what do you need to do? Explain me the steps or find it. How do you find Brian's predicted height? Do it. Go ahead and do it. Great job, Marley, right there. Yep. Find my prediction. So a residual is how much the model misses by. So when you think about a residual, and I'll show the steps right here to think about what a residual is. A residual is when you have a line, and if the line is the prediction, means it's a Y hat, and then all the dots are actual Ys, this would have a negative residual because the line overestimates it, and it's below the line. So there we go. Braden's showing the math right there. So you have to take in the formula and get predicted height. If anyone wants to solve the predicted height, I'll start writing it out, but just tell me what this solves out to. So Braden wrote out, you would take the formula down here to put in Brian's weight, and then you would solve this. It's probably gonna be like 70 or something like that. So we're just plugging in the numbers, 185 times 0.073 plus 56.34, basically 70. Nice job. Yeah, there's my predicted height. So Brian is what to his prediction? I can tell you the residual right now. The residual is 5.155. How did I get that? So in terms of the model, my residual is like this. That's the way it looks because Brian is what? There's my residual. Observed minus expected, pretty much, or actual minus predicted, I call it usually. I just say residual equals actual minus predicted. So the residual of 5.155 is equal to the actual height of 75 minus the predicted of 69.845. So exactly, great job right there, David. Sorry, the writing got a little bit small right there. Please ask me if you're stuck. This is the predicted. Brian's actually this. So what does that residual mean? What does that residual mean? I'm gonna draw it over here again. What does this residual here mean? So can anyone tell me what it means that Brian has a residual of that? What does that residual mean? Because there's Brian right here. Here's Brian's residual. So what does that mean? Ah, Marley, it's a bit interesting. So the line is the estimate, remember? So the line is the estimate, and then this is the actual, and the residual is 5. We'll just call it 5. We'll just call it 5 for brevity. So you could say the prediction, if you want to make it easy on yourself, was 70. To make life easy, we're just going to pretend it's 70 by rounding. And then the residual is going to be 5. So when you go here, just for ease of numbers, residual is equal to 5, where Brian is actually 75 minus 70. Exactly, I am that much taller than the prediction. Would it say in the question if it wants us to find the residual or the, questions will say like find the residual, find this or that. And then Marley, funny enough, when a residual is positive, the model underestimates. So positive residuals, because the model is the estimate, and there's the actual, like this is Brian's actual height on the dot, and the model is like a line making predictions. So if the residual is positive, the line underestimated. It's counterintuitive, and a lot of my Pearson questions get missed with that. So you have to think if you're above the model underestimates you. So positive residuals is when you're above the model. So we love asking questions like this. I swear this is a teaching to the test moment. What is bigger if a residual is positive? So if a residual is positive, what must be bigger? And look at the screen or draw it out on the test. You can't bring notes. I think I'm going to move my office hours to online today from 2 to 4-ish. Maybe I'll stay on campus. And so if a residual is positive, what is bigger if a residual is positive? We'll let a few votes come in. And you can see it with the drawing. Oh, I can't wait to be 100% again. So are we ever 100%? That's the question. So good work. Everyone got it in the chat right here, it looks like. So let's go. Let's get some points. You see it right here. If a residual is positive, the actual was bigger than the predicted. So does that make sense visually? Like you're looking at it, like this is a positive residual of 5, meaning someone was 5 higher than the prediction. That's what a residual shows you. If you do it a bunch of times and do the formula, you know actual minus predicted. Like, and you can just think actual minus predicted, if it comes out positive, would be the actual, which I've highlighted and hovering over right here, has to be bigger. Is it making sense when you see that? And you get this formula on the test. So if you know it means residual equals actual minus predicted, Monster will fix you. I hope, Braden. I hope. Get that monster energy. I'll tell you what, the guava is really good. Did you tell me to get guava, Braden? You started a new addiction, man. It's good stuff. It's good stuff, this guava. It might be a new flavor or something. My hair's all floopy. Oh, is that a guy drinking Monster? Dude, we got to put that as a Mubot quote. I don't think it was me. Well, someone I owe thanks to, or I should. Braden, we got to make that a quote of the day. What should we talk about now? What topics do we want to talk about? Does I make this a quote of the day? Braden getting a quote of the day right here. Quote. Oh, no. Mubot can't do the face. He can't do the face turquoise drinking coffee. He can't do it. He won't do it. There's some emojis he won't do. What should we talk about? We'll fix you. Monster will fix you will be the quote. Can you explain the difference between conditions of sampling distributions? Yeah, let's talk about the conditions. Code 487, Monster will fix you. Code 487. Can you explain plot thickening? Yeah, let's do all conditions starting from the beginning. I think Marley has one too. Statistical significance. Okay, let's do that. Let's do, I'm gonna put notes in here so I remember which ones to do and in what order. Okay, we're gonna do 31, 23, stat to 1, regression, conditions, and significance. Conditions for sampling models. Okay, here we go. Okay, let's talk about conditions for regression. So we're starting with the regression conditions. And to check the regression conditions, you just have to memorize QQ, straight enough, no outliers, plot doesn't thicken. So what we're going to do is we're going to talk about each one of these conditions and how to check them. So the first condition here, QQ, means what? The first condition here, QQ, means what? The first condition, QQ, means what? What does QQ mean? Like, I make you memorize QQ straight enough, no outliers. Two quantitative variables. And so we're going to draw right over here. I'm going to try to write small enough that I can do it. We're going to have right here if it passes or fails. Pass and fail. So when you pass this condition right here, the two quantitative variables, what you would see for two quantitative variables when you pass it is you would see a scatter plot. So if we have something like height and weight, whatever order we want to do it, it'll make a scatter plot. If you have something like class level and GPA, why can you not do QQ with class level and GPA? You get side-by-side box plots. So class level, we'll go class right here, class level like freshman, sophomore, junior, senior, and GPA will not meet QQ. Why does class level and why does it not meet it? Class is categorical. So you'd get side-by-side box plots for that. So you can't do regression. It just means you're doing something else. So the two quantitative variables right here, you have to have two quantitative variables. So does that make sense? Class is categorical. So if anything asks, can we do regression? You got to say, is it QQ straight enough? No outliers, plot doesn't thicken. There are questions that ask you where sometimes it gives you categorical and you're like, no, we can't do a regression on that. Can't do it because that's not categorical. So watch that, or that is categorical, can't do it. Straight enough means that the data what? What does straight enough mean? It's not perfectly straight. It's the straight enough condition. What does straight enough mean? The data is basically what? Basically does what? Kinda-ish does what? Basically linear. It doesn't mean perfectly linear. It doesn't mean perfectly follows a line. Kind of follows a line. So I'm going to draw one right here that kind of follows the line. You notice me, whatever. So you notice there's some weirdness. You notice it's got that little bit of weirdness right there. It's straight enough. Does that make sense? Basically a line. So we get a little bit mad. Like if it's got a little bit of weirdness, this is actually the pass because you give it a little bit of a pass. And some statisticians might get mad at me and say, that's a sigmoidal model, S shape. You should fit the exponential models to that. And I say, a line does good enough. A line does okay enough. Sure, we could do better. All models are wrong. Some are useful. George Box, take that stats person critiquing my stats. That's good enough. But there are models that don't work. Caitlin, good question. So this is where it's not straight enough. And I'll even give you a test question related to this. So this is where it's not straight enough at all. If you fit a line, it's flat. And the whole thing is just not a linear model. The whole thing. This is super bad. So let me ask you this question right here. Our correlation of 0 means there is no relationship. And it's kind of more of a test one question. Yes or no? Correlation of 0 means there's no relationship. A correlation of 0 means there's no relationship. So answer really quickly right here, because we'll go on. Don't worry about getting it wrong. A correlation of 0, Ooh, it's flipping between a correlation of 0, and the answer is no. It'll be pretty obvious, yeah, Kenai. A correlation of 0 does not mean there's no relationship. So the answer would be correlation of 0 means there's no relationship. That'd be no. Because a correlation of 0 means there's no linear relationship, because there can be parabolic stuff. So when we try to look at a relationship and we fit a line, sometimes the line doesn't fit. And so there are relationships that are non-linear in nature, like this one right here. So this means you can't fit a line to it. It doesn't mean it doesn't have a relationship. It means fitting the line is the bad idea. Does that make sense? Like when we do regression, we're fitting a line, so we want it to have a linear form. This one is straight enough, and this one right here does not follow a line, so fitting the line doesn't properly express the relationship, so doing linear models on it is a bad idea. Modeling means to describe it with a line, like to model the relationship with a line, to say, hey, this follows a line. No, it doesn't. We should use a parabolic model. Or do people understand the straight enough condition, which means it basically follows a line. The data points basically follow a line. Not perfectly, basically. Now, the no outliers, we make super obvious on the test, and especially for 201, we make it really obvious. And the no outliers, if there's no outliers, you're going to see a nice, neat relationship here that looks like the following. And there could be a little weirdness, little far away, but we'd probably give you something like that when there's no outliers. There can be points that have a little deviation. That's perfectly fine. That's not a big outlier. It's just fine. It's fine. It's fine. Does that make sense? All those points right here, this is the, yeah, you're fine part of the plot. Those are all fine. If we're going to give you an outlier in 201, when we teach you the basics, we're going to go right here. We're going to have a model. And then you're going to see like, boop, 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 boop. And then you see, oh my God. This is going to be really bad. You're going to have something way far away. Now, I will mention this super briefly. We do have ways to analyze this in higher level statistics with things like influence plots. So if you're ever wondering, like, how would you know if it's a, oh my gosh, I can't do it today. Yeah, there we go. Yeah, we got problems with these rows. So I can find the points rather quickly using higher level statistics. Yeah, I love when it's obvious too. Yep, we will make it very obvious on the test, but we do have ways with statistics to measure the leverage and the deleted studentized residual and the Cook's distance, or that is Cook's distance, that is correct. We do have ways of measuring the influence of these points and to see how bad the outliers are. And we don't teach that in 201. You get the basics of like, look at the plot and see if it's really far away. So an outlier is something that deviates from the trend. We won't make it a small one. We'll make it an obvious one. So the no outliers condition, look for things that are extreme. Plot doesn't thicken. So what you need to do with plot doesn't thicken is you need to look W201 right there. Plot doesn't thicken. You need to look at the what plot. When we say plot doesn't thicken, no outliers is pretty self-explanatory. There's no outliers. Look at the residual plot. We don't want it to thicken. We don't want it to. Some people say plot thickening or something like that, which is a bad thing. We don't want the plot to thicken. So what you want is actually what is called homoscedasticity. Homo meaning same. And if you take that line I just drew and made it flat, then what you would see right here is the dots around it are going to look like this. I'm going to try to draw that same relationship. And this is called a what plot, where you set the line equal to 0 and you see how far away the points are. And you want it to have about the same thickness throughout. Thickness is spread of data around the model, which could also be measured here by looking at this. It's easier to look at a residual plot. Great job, David, right there. So the residual plot gives us an idea of does the model have about the same equal spread throughout? This could also be called equal spread or equal variance condition in other classes. So now you look at where we fail, and you got to be careful because people say we don't want the plot to thicken. So is the following a good or bad plot? Remember, it's the plot shouldn't thicken, and that usually confuses people, and I might have just tricked you. But I'm going to draw it this way, and we don't want the plot to thicken. So is this a good or bad plot? And if you know the technical term of homoscedasticity versus heteroscedasticity, you know that this is heteroscedastic. Heteroscedastic, this is horrible. Heteroscedastic means differing spread, heteroscedasticity. And you don't want heteroscedasticity, you want homoscedasticity where it has the same spread. So to check the plot doesn't thicken condition, you want to look at a residual plot and see that it has about equal strength throughout or equal spread throughout. So here are the 4 regression conditions. QQ straight enough, no outliers, plot doesn't thicken, all shown to you visually when we fail QQ, when we fail straight enough, when we fail the no outlier, and we fail plot doesn't thicken by looking at the residual plot. That is the 4 conditions for checking regression in Stat 201. Okay, we have statistical significance. Let me mention this right here. I'm going to put this as a new section. So thank you, everybody. So it has nothing to do with how many points there are. It has to do with the spread of the points, like how much they spread out. They should have about equal spread throughout. So if I were to make a residual plot of this, so let me grab my residuals plot, residuals of, residuals of my model. Yeah, what do you think? What do you think? Does that have about equal spread throughout? Does my model have about equal spread on the residuals? Go to check regression. Does my model have about equal spread? Yeah, it has about equal spread. There are maybe some outliers-ish. You got this point down here, you got this point down here, you got this point over here, and that's actually showing up in the influence plot. This is a little more technical of a one, but if you look at this right here, it's more of an outlier issue with this. So if we gave you this plot and we said, does this residual plot look good? You'd go around it. We'll do a nice yellow to mean good. And you'd be like, yeah, that's pretty good. And then maybe you just got the outliers over here. There's 2 points right there seem to deviate, but it looks to have about the same spread. And once again, I'm doing more technical ways of analyzing where then I can identify the different points, the 3 different extreme points. And if you look at our graphic, remember the 2 that were below and the 1 above? That 1 above is that point right there. So it's showing up in another plot. But for 201, remember, you're just seeing if the plot has about the same thickness throughout. And what plot? The residual plot. So hopefully I'm throwing a little like higher level knowledge. I hope it doesn't confuse everybody. How about that statistical significance? Catch me outside, talk about statistical significance. How about that? That's what I say. Significance. Significance always means look at the what? Significance always means look at the what? Answer, bottom of the screen. Significance always means look at the what? P-value, Caitlin knows right there. Good to see you, Clay. P-value right there, always look at the P-value. Now, the significance of a model is the significance of the slope. Do everyone hear that? The significance of a model is the significance of the slope. How do we know if a model is statistically significant? In regression, to know if a model, which is actually this P-value down there, and look, it's the same as the what variable. To know if a model in regression is statistically significant for technically simple linear, which is 1x, we look at the p-value of the what. This p-value down here is actually what is called an ANOVA, which is the test of the whole model, and it has the same p-value as the slope. And so it'll be that the p-value of the slope is less than or equal to 0.05. The p-value of the slope is less than or equal to 0.05. Notice how down here, the significance codes give you stars only when the p-value is less than 0.05, as in this is kind of significant, very significant, super duper significant. So something is more statistically significant, the what are the p-value. So looking at the codes, something is more statistically significant, the what are the p-value. As you see here, it gets more stars, the what are it gets. Closer to 0, smaller. So why smaller? Well, if I were to create for you a relationship that is likely by random chance, I can do it right here using our norm. This creates 100 observations which are random. And we'll call this x, and we'll call this y, and we'll do random normal numbers. Now I'm going to look at the relationship of a random x and random y. And so with looking at a random x and a random y, it's going to look completely random. Whoa. It actually has a little bit of a slope. But that slope is actually due to random chance. It didn't come out statistically significant. Do you see right here the p-value? Even though it slopes down, this small dip is probably just due to what? This small dip in the model is probably just due to what? This small dip in the model, because the p-value is higher. So if something has a p-value of 0, would it be a normal curve? Ah, Elizabeth, really good questions. The first time we learn p-values is to check normality. This is different. This test right here is to see if there's a linear relationship or not. Every p-value is associated with a certain test. The p-value here is to see if the slope is equal to 0, versus the first time we did p-values was to see if the data is normal. So what you're thinking of, and really good memory there, is when we run this test, we'd be asking, is the data normal? So this was the first time we saw p-values. And tell me, let me do a crazier one. Does this data look normal? This is a review of chapter 5 right now. Does this data look normal? Just yes or no. Does that data look normal? Yes or no. Does this data look normal? Yes or no. Does that data right there look normal? No. So when I run the test to ask, is it normal? The p-value comes back low because we reject normality. This is a Shapiro-Wilk test for normality, which only looks at, is the data normal? Versus when we make a linear model, we also get p-values. P-values are used all throughout statistics. So p-values don't just test normality, they can also tell you if the slope is significant. So this p-value right here is associated with the x variable in this model. It has nothing to do with normality. It's only asking, is the x significant? And the null hypothesis is x is not significant. Now, a what line would be the least significant line possible? And I'll try to generate it. A what line would be the least significant line possible? I kind of got it there. A what line would be the least significant line possible? A what line? I could try to get closer, but this one's pretty darn good. The least significant relationship. Kind of a flat horizontal line. Does that make sense? Horizontal is the least, because then if you go across x, there's no real difference in y. And look, the coefficient of x is basically 0, and the p-value is super duper high. Meaning we don't think there's a statistically significant relationship between y and x. So when you look at the p-value in a regression model, the lower the p-value is, the more evidence of a relationship we have. Do you think that you can predict someone's height to some degree by how much they weigh? Do you think you can predict to some degree somebody's height by how much they weigh? Like if I have a friend who weighs 90 pounds and I have a friend who weighs 200 pounds, do you think you could maybe use that to make predictions? Yeah. And that's because weight is statistically significant in explaining height, meaning its relationship is unlikely by random chance. That's what a low p-value always means. Whatever we're seeing here is unlikely by random chance. You can say that for any p-value when it's low, i.e. statistically significant. True. And you know what we could add to this model? We could also add in desired weight. So you could ask somebody how much they want to weigh and make a multiple regression model and use that. So now we're into multiple regression with multiple x's because we ask people their weight and their desired weight. And if you take a look at this model, both of the variables, weight is not significant and desired weight is, and the interaction between the two are significant. Let's just do a non-interaction model. As you can see, there we go. So both the variables are significant in this model. But we could talk about multiple regression and all those cool things, but 201 does not cover multiple regression. But that, Brain, is a really good question because maybe there's more variables, more x's, more lurking variables. So do people understand what statistical significance means? In a regression model, it means that x and y have a real relationship. So to review, statistical significance in a regression model means x and y have a relationship that is unlikely by random chance. The unlikely by random chance phrase can be said for any p-value that is low. It's that if you go back to the normality thing, the relationship we see here is unlikely by random chance given the data is normal. So assuming that the data is normal, we wouldn't see a distribution like this. So I reject normality. I have evidence it's not normal. Using statistical lingo for this summary, the relationship between height and weight is unlikely by random chance, meaning I think there really is a relationship here, not a random relationship that is nothing. So here's a random non-relationship. All of these are technically random non-relationships. I'm just trying to find the most random, the flattest of lines. You can just look at, there we go. Notice when the line is really flat, the p-value got whatter again. With that very, very, very flat line, the p-value got very what? The p-value got very what? Meaning a not significant slope. And also the coefficient of x got towards 0, which means flat line. Oh, no one knows? This is one of the highest p-value. There, I said it. High p-value means not significant. X and y do not have a relationship. What's interesting is if you keep high, if you keep doing this, you will find something statistically significant by random chance, as in a type 1 error. So if I keep, wait a minute, that was the highest we've seen. That was almost 1. Yeah, and if you look at that, that is almost perfectly flat, which then the coefficient is basically 0. If you keep doing simulations, you will find something statistically significant by random chance, i.e. a type 1 error. Because 5% of the time, you can get things that are significant by random chance. And trying to find one that is randomly significant because it can happen. You just make an error. Man, we're not getting it. There's another really high one. Dang, we're getting all the high ones. Can't get one low one by random chance. We're getting close. I just really want a statistically significant by random chance one. Because these are all random. Oh my gosh, that was almost perfectly won. That is one of the highest ones I've ever seen when I've been doing these simulations. And look, the X coefficient is basically 0. We got one more thing to cover. I know I'm just having some fun for a second. I really just want to get one. I can't believe I get almost 1 and I can't get a low p-value. Could do a for loop and have it do it for me. 10 more times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I just got another crazy high one. Anyways, all right. I can't find one that has a low p-value by random chance, but it does happen randomly. Oh my god, there it was. Man. There's a statistically significant by random chance. Okay, conditions for sampling models. I'm gonna also have to make the video here. What are the conditions to do the sampling model of the sample proportion? What are the conditions to do the sampling model of the sample proportion? What are the conditions? Random, 10%, random, 10%. I love randomness too. I love random too. Random, 10. And then you pause. You got to pause and do success failure. Random, 10%, success failure. Random, 10%. I think we're on class 20. Success failure. So class test review day. So I'm going to write you a problem here right now, and you need to check all the conditions and do them properly. The problem is people get to the conditions and they always say success failure because it's one of the first ones you learn after you do random proportions. Thank you, Marley, right there. Marley, you rock. Thank you so much. Okay, so I'm going to write you a question right here, and you need to check all the conditions. Okay, so let's go back here, run the conditions, and here we go. Okay, Brian goes outside the library to talk to students about what they think about parking. There were actually people doing that yesterday. He randomly talks to every 5th student who walks by. He talks to 50 students in total, and 40 think we should build a new parking lot using athletic funds. Okay. I mean, I'm sorry, athletic. They make a lot of money. That's what we're gonna do. I'm saying we're doing it, so it's happening. We're not doing it. I don't know. It's tough. We only have so much land at UT. I would not want to work parking. We only have so much land. It's tough problem to work out. Condition 1, do we pass or fail it? We got about 10 more minutes. Condition 1, do we pass or fail, and why? Random. You need to ask yourself, does the problem indicate that we randomly selected people? Observations. I want to get some Taco Bell. Yeah, Brian says and we'll highlight what in the problem says that. So, and what kind of sampling method did I do? So we pass. What kind of sampling method did I do? Does anyone know what kind of sampling method I did? Little chapter 10 review, systematic, every kth observation. Great job, Key9, everyone there. So we did a systematic sample from a random starting point, every kth observation. Wow. Owen Wilson, wow.
Wow.
Yeah. 10% means our sample size n needs to be less than 10% of the population of n, capital N. Okay, do we pass 10%? Do we pass 10%? Yes or no, do we pass 10%? And why? Explain to me in a full sentence. People are getting the right answer. People have the right answer. This problem does not tell you capital N. Problem does not tell you capital N. You just got to think it's UT. So, and a lot of people get this wrong because they start misidentifying in the problem. When you do the problem, this is lowercase n, this is x over n equals p hat. A lot of people start using p hat. 50 is less than 10% of all UT students. UT has a huge population, exactly. So great job, Braden, right there, because UT has like 30,000 plus students. So it's way less than 10%. So the answer is we would take n divided by capital N. And for this problem, that is going to equal 50 divided by 30,000, estimating that. And that is way less than 10%. Now, last, we have parking believes. Sure. Okay. Had to add in one more thing. Know your notation. Had to add in one more thing to be able to solve this. And Braden is right. Pause. Got 3 some points for pause. Everyone says success, failure. So what's the third condition right here? Everyone always goes success, failure. Because that's the first one I learned. It's success, failure. So what's the third condition? What is the third condition here? Everyone always says success, failure when we get to the third condition because it's the first one you learn. But we are doing these in order by which you learned them. Trying to trick you. Like, everyone says it. 10 successes, 10 failures. It is success, failure. Which states we need at least 10 successes and at least 10 failures. At least 10 successes. And it is met. Ooh, is it? Is it? Is it? I played some tricks on this, Marley. I played some tricks. Gotta sneeze again. Do Office Hours Online again here. Is it met? So for success, failure, you need NP greater than, not uppercase N. NP greater than or equal to 10. NQ greater than or equal to 10. What do we have to find that's not marked right now? It is not met. I played some games here. So that would be the observed. We have to do expected successes and expected failures. This one's a bit of a tricky one. Like, this is a mean version. To solve this, you need to find P and Q. P is equal to 0.90, and Q is equal to what? For the success failure condition, you want at least 10 successes. Good job, Clay, right there. You are right. Q is 0.10. So when you solve this out, you get right here that NP and Q, we'll go right here, is going to be 50 times 0.90, and that is equal to 45. You know what's really cool? What's this answer going to be? That this one is 45. You can actually quickly solve. You don't even have to do the math because NP and Q have to equal to N. So you can see if you have a sample size of 50, you expect 45 successes. And I'll throw you some big things. It's going to be 5. There you go. So you actually fail because of this. I was a little bit mean here. You don't have at least 10 successes, at least 10 failures. Why do we check conditions? Why do we check conditions? Why do we check conditions? The whole point of checking conditions is to see if what? Correct. Both need to be at least 10. NP and Q mathematically need to be at least 10. See if the distribution is normal. Not normal. Kind of not normal. Now you'd have 40 successes, 10 failures. Normal. The more balanced out the successes and failures are, the more normal it is. If you go down here to like a 1% success rate, not normal, not normal, not normal. Doesn't look normal because you now have 1.5 successes and 48.5 failures. Let me ask you this. Last 2 questions right here. To calculate P hat or Y bar, we must meet the conditions. Yes or no? To calculate P hat or Y bar, we must meet the conditions. Yes or no? I need to send an announcement. Say I'll be doing online office hours today from 2 to 4. Then I got a meeting at 4, so I'll just hang out. Maybe I'll get some lunch on campus. I'd like for you to try to calculate P hat right now. Let's say there's 10 people in a room and 3 of them own bunnies. What is P hat? There's 10 people in a room and 3 of them own bunnies. What is P hat? Marley, you're on the right track. Marley, great job. There you go, you did it. You don't check conditions, you just do it. 30% of people have a bunny. Let's say I spend $30 on a meal and Chelsea spends $40 on a meal. She got the extra cool steak. So what was the average amount spent between Brian and Chelsea? I spent 30, Chelsea spent 40. What was the average between Brian and Chelsea, which is y bar, the average? So I want you to 35. You just averaged them. Did you check any conditions? No. So did everyone see that? You didn't check any conditions. To compute the average, you just average things. There's no conditions to average things. It's like, don't worry if you got it wrong. But to do the average, you just average things. We check conditions to see if the distribution, as Marley said right there, is normal. The whole point of checking conditions is to see if things are normal. You don't check conditions to compute the sample proportion, which is 3 out of 10 people own bunnies, or the sample average, which is white bar, which is Chelsea spent 40, Brian spent 30, 35 was spent on average between the two people, because you can just average numbers or find out the proportion for samples without any conditions. The last condition, which we'll mention just briefly before class, is going to be the same things right here would be done, but we would now have the success fail. We would now have the large enough n condition. The large enough n condition deals with quantitative data. The large enough n condition deals with quantitative data. So large enough n. It's more complicated. I'm going to have to change the question a little bit here. I think so. They don't like it. If you can get the link, yeah, sure. That's my best comment on that. We should do it like a public class. It's unlisted links. Thank you, Caitlin. I'm honored by you saying that. And I'm going to have online office hours again between 2 to 4. It will be recorded. So between 2 to 4, I'm going to do online office hours today. So if you can't come to class, because I'm not a finished one in the class, but it's generally considered, I like teaching. I like teaching. So large enough n. The sample size, or wait, let's do it in steps. 1, what is the original shape of the data? So it'll either be normal, skewed, really, skewed, or very skewed. What is the required sample size? Really? We'll go to a new page on this. So the required sample sizes are either 1, 25, or 30. Is our sample size at least this large? No class, where can I find your regular office hours? Any YouTube live right here, any YouTube live, and email me. Thank you, Braden, right there. Yep. The live tab on YouTube has all of them, and we have a lot of other links. You can ask for links and stuff. And the review also has a lot of stuff, and honored by people coming by, swinging by, getting help, drinking Monster Energy with me. So the question would have to read, he asked them how much UT should charge on average a semester for parking reports students want to pay $100. I don't even know if that's even close to what we pay. But when normally 12, so in-person office hours when I'm feeling a little bit better is 12:45 to 2:15. Online office hours are always 10 to 11. I might get in here at 10:05. Sometimes I'm walking around. Had some really great conversations this morning. So usually 10ish I start, and then I'm sometimes a little bit earlier. Sometimes we stay a little bit later because it's supposed to go to 11. So it's between the 10 to 11 window. So I try to stay as long as I can, and then I get ready for the other stream. So thank you so much for swinging by. So with this right here, so when you check this, you're actually doing the central limit theorem. So to know if we meet the large enough n condition, what would you need to look at in this problem? See you, Marley. See you later. Yep, just stream back between 2 and 4. So what would you need to look at in this question to see if we meet the central limit theorem? What would you look at in this question to see if we meet the central limit theorem? Well, the first thing you have to look at is what is the original shape of the data. So large enough n is used only for quantitative data. Notice the third condition here is different. Exactly, and Marley even says the central limit theorem states that the distribution of the mean will get more normal and tighter as n increases. So those are the two things that the central limit theorem states will happen. The mean stays the same, mu y bar equals mu, but the standard deviation gets tighter by a factor of the square root of n. The large enough n only applies to quantitative data like how much should students pay for parking as a quantitative versus do you like parking on campus. But the other two are same random and 10%. That is correct. So when doing sampling distributions, the first two conditions are always random, 10%, and then we pause. And the reason we talk about pausing right here is because it's going to be a different condition based on if it's cat or a quant. Categorical will be success failure, which we just did a moment ago. And the quantitative, which this question asks the amount spent, pause in the chat, is going to be, thank you, Braden, right there. Then the quantitative large enough n is checked this way. It states that the original distribution of data is skewed. So is a sample size of 50 large enough? Unfortunately, I can't simulate 50, but I can simulate 25. And the distribution of the means of sample size 50, we'll pretend this is taking 50, will be more normal and tighter because we have a larger sample size to make the sampling distribution. And if you take a look, does that look pretty normal? Yeah, it does. And the reason we meet the condition is, well, we have a skewed distribution, not heavily skewed. The problem states that the data is skewed a little, which would fall under skewed. We have to have at least 25, and for our problem, 50 is greater than 25, or equal to, technically. And so you look right here, and you see we took a sample size of 50 students, or it said it previously, there's the 50, I might have deleted that portion. But if the problem says we took 50 and it's skewed, 50 is a large enough n, large enough sample size, such that the distribution will be nearly normal. Let's say we only talk to 2 students on campus. This will be the last question. If I have a very skewed distribution, would a sample size of 2 be large enough such that the distribution will be nearly normal? Is a sample size of 2 large enough if my original data is skewed? No, look at that. It's still skewed. As you increase the sample size, it becomes more normal and tighter. And it's amazing that the central limit theorem starts to kick in even only at this. Some of my Pearson questions get into this, showing you that sometimes you need very large sample sizes. So 2 would not be large enough, and maybe I didn't make it skewed enough. It's kind of shocking how the central limit theorem fixes things. With that, we're going to head out, and I'm going to start class very soon. Bye for now, everyone. Bye.